Trên honeymoon couple.
Good afternoon, sir.
Good afternoon, everyone.
Good afternoon, sir.
Good evening.
Hello, welcome to the session.
Good afternoon, sir.
Okay. Stuart is there, Stuart?
Hi, how are we?
Okay. I once again welcome all the participants on behalf of Regional Science Center. I welcome all participants once again. And I think this session is quite interesting. Even I don't have any idea what is Stuart is going to disseminate. And I think it is kind of mythbuster session, I think so. And there is a many so-called myth in the science. So there is a knowledge gap between original facts and known knowledge to us. So sometime we have to make the bridge the gap between the knowledge and the myth. I hope Stuart is going to something is very great session. I think it will be, and so he will supposed to bust the different myths in science. And afterwards, that session will be concluded at the 4:30 p.m. I think so. Afterwards, I request all participants to stay tuned at our Zoom session. We have only near about 10 minutes concluding and valediction sessions, and this festival has been organized with support from the Australian High Commissions and the Odisha Vigyan Academy, and the persons those are supporting our endeavor, they are supposed to come at the valediction program. I hope our participant will remain stay in the session. And I would like to request Dr. Stuart to continue the session.
Certainly. Look, thank you very much for the introduction, and again to everyone, thank you for coming back for today's session. I just noticed we've got slightly fewer people here today than yesterday, so I'm just wondering whether or not lots of people were coming yesterday, hoping that we're going to explode things with chemistry. Hopefully, those of you which came yesterday got a little bit of your brain exploded, thinking about some of the things which we were sharing and the questions that I left with you. Now, in today's session, I'm going to try and focus on just a few questions, and we might go a little deeper with those. And as my good friend said in the introduction, there are a lot of things we think we know, and a lot of things which get shared with us, our teachers, our friends, our textbooks, things that we think are true, and lots of them are true. But sometimes in amongst that mix, we get told things which are explanations. They kind of sound truthy. They sound as if that makes sense. And sometimes they are right, but sometimes they're also either misleading. They make us, what they're saying might be true, but they may get us to think in a way that is not quite right. And sometimes they're just plain wrong. And so tonight we're going to look at some activities, and I want you to share with me what your thoughts are. So don't be shy. Many of these things we've been told, and we haven't had a chance to think about. Let's start with the first one, which I know from the time I've spent in India is something which is either done in some schools or shared in some of the textbooks. And it's when we're dealing with the idea of atmospheric pressure and chemistry, and we talk about the weight of air. We talk about air has a weight. And that's a very important concept. It leads to air pressure and a whole lot of important things in science that come from understanding air pressure. But that starts with our understanding about air having weight. So the first activity that I'll set up tonight, I've just got a very light, thin stick, which I've set up for you there. Just making sure that's visible. Yep. And the activity that would normally happen or normally be described is to go and put a couple of balloons up there, get them balanced, and then see what happens when we let the air out of one of the balloons. So that's what we'll do as our first activity. If one of my participants could just blow up that balloon for me, and I'll blow this one up. It's only fair that we share the effort. Someone just holding up the camera, if you all blow very carefully. Doesn't seem to be working. All right, I'll blow both of them up. I think that's big enough for you to see. All right, I'll tie that one off. I hope someone was counting how many breaths I put in. And you were counting? That's pretty good. I think it was 5 or 6. I think it was 5 or 6 breaths. So I'll just grab a clip, just hang the balloon there for the moment. It's not going to do very well. And I'll grab the other balloon. It's a shame that you weren't here to blow this one up. Let's see if they're about the same size. I think maybe one more breath. Okay, tie that one off. Oh! That's always the problem when you're doing live science. Things go wrong. That's all right. They don't have to be exactly the same size. I will balance the balance anyway. All right, let's bring that down. Oh, come on, behave. All right. Now let's just get this balanced. And you may all have seen and done this activity before. I do want to try and get it as balanced as possible. Now a balance this big can probably spot the difference between less than 1 gram, probably easily less than a gram, probably down to about 1/10 of a gram. If you want to wait. Let's see whether I've got it more or less balanced. It's close, but I think the far balloon is still tending to be up. Now, let's see how we go. All right, I think that's pretty good. That's pretty good now. It's a little bit of seesawing. We'll let that dampen down. So my question to you, which I'm pretty sure you're all going to get right, is we've got the balloons balanced. They're both full of air, pretty much the same amount of air, but we've got it balanced anyway. What's going to happen if I let the air out of one of the balloons? What do you expect to happen if I let the air out of one of the balloons?
One
The
side.
other balloon will go down.
It will go down.
So which one goes down?
The one from which the air has been taken out.
So if I let the air out of this balloon, Will it go up or will it go down?
Go down. It will go down.
Sir, up. Sir, up. Sir, it will go up. It will go up.
So we're going to take
Down.
all of the air down. So we'll let all of the air out,
Sir, it will go up.
go up.
Sir, up.
Okay,
up.
everyone. I love data. I love data. I'm a scientist. So everyone hop on the chat box, the chat window, and put in your guess. Up or down, okay? I'm talking about the one I let the air out of. So the one I let the air out of, does it go up or does it go down? We seem to be getting a lot of different thoughts. And I like that. I like that. It means some of us are in for a surprise. So that's a good thing. Some will go out, it depends on how it goes out. All right, that's lots of different ideas. Up, down, up, down. Wow. I love working with people because you always surprise me. Okay. All right. I'm going to find my cutters. And what I'm going to try and do is just cut the top of the balloon so I don't lose any rubber. I don't want it to pop, but I want to let the air out, okay? So let's just make sure that it is balanced. And I'm always trying to do good science. I'm always trying to show what good science might look like. I think this one is still just a little high. It's very, very sensitive. And I don't want you complaining afterwards that this wasn't a proper experiment. That would be terrible. All right, I think they're balanced. I'm going to let the air out of this balloon. I'm just going to cut the soft rubbery bit up here. And I really, really hope it doesn't pop. Because if it pops, we got to do the experiment all over again. All right, good cut. Lots of air coming out now. If I let it go, we'll actually see something else happening. We'll see a couple of things happening. At the moment, I wouldn't guarantee what you're seeing is what's really happening, because as the air is coming out, it's like a Newtonian engine. It's throwing air in one direction, so it's like a jet. Every force has an equal and opposite. So if the air is being pushed this way, the balloon's being pushed that way. We're doing two bits of science at once, so that's good value. But as the air is coming out, that's going down. As the air is going out, that's going down. That looks pretty poetic. I like that. That's interesting science, but it's also pretty beautiful. I like it. All right. All right. So at the end, when it finished pushing the air out, we're not dealing with any rocket science. Now we're just dealing with the balance. Let's have a look. And it really is why you have to be, with this activity, you need to be really sensitive. But I think now you'll see, even using the big balloons, we've got, this has gone down. This has gone down. Not a lot, but it's gone down. Now, if you look in your science books, many of your science books, they will tell you this demonstration shows you that air has weight. So there's air in this balloon. There's no air or very little air left in that balloon. So this balloon is heavier. And they use this activity as a way to tell you, to describe, to demonstrate that air has weight, has mass. In this particular case, it shows it has weight. All right. So that's what they would do with that activity. The only problem is that's not the right explanation. That's not the right explanation. Air does have weight, but that demonstration really doesn't show that, not properly. What's wrong with that demonstration? Can anyone see something wrong with that demonstration?
There's the
A reason?
rubber.
Lengths are not equal.
But we had them balanced anyway. So the weights, even if the weights weren't exactly the same, the balance was balanced. And we let air out of this balloon and this went down. So there is a net force.
There's the
on there,
rubber
which is-
balloon.
Sorry?
There's the rubber balloon.
I'm not sure. Can you give your answer in a
It's,
different way? I'm not sure what you're saying.
It's not just the air, it's a rubber balloon as well.
But we have the two balloons. So the two balloons are the same. And the weight of the balloons, even if they were a little bit different, we balanced them at the start. So that's a fair, we didn't change the amount of rubber. So we balanced
can
them
I
at the
tell?
beginning. Sorry, say again?
Can I tell?
You can give your idea, yeah.
Sir, the balloon in which the air is present is going down by atmospheric pressure.
Where is the atmospheric pressure on which balloon?
On the balloon which has air in it.
But the air pressure is here and here. So the air pressure is the same on all sides. It's true, there's a very little bit of difference. The air pressure in the bottom of the room is slightly higher than the air pressure here. And I can actually measure that difference. I can measure that much difference in air pressure, but that's not the reason. But that's a good thing to think about. The balloons have changed size and shape. And this is the thing when you're exploring new ideas. And for you, this is a new idea. It's always important to think about all of the things which have changed. And the shapes have changed. And so that's something we'd need to think about. But that's not quite the reason. So let's look at something else, something similar, something which they don't show you. So I'll take the balloons away. Does anyone want to take that balloon home? Just put your hand up. We'll have that sent round to you. In times of COVID, it will take a while to get that delivered, but we will send you the balloon. All right, I'm going to change the activity, but just a little. Just to go and help us explore what might be going on. Because the activity we just did isn't completely wrong, but as I said, it is very misleading. Let me just get these clips back on. That balloon no one wants because it's got a big hole in it. All right, so I've now got two plastic bags. These are kind of like lunch bags here in Australia with a zip seal. We can seal them off. So they're kind of same as the balloons. They're about the same size as a balloon. We'll just go and get these balanced again. Currently they're both empty. It's a pretty good job of balance. They're not far. I think they were better before I tried to help. That's often Okay, that's pretty good. It's pretty good. All right. Now what I'm going to do is I'm going to inflate one of those bags and seal it again. So in the previous activity, the big balloon, which had all the air in it, looked as if that was heavy and it sank down. These two bags are now balanced. If I get out of the way, you can see they're pretty balanced. That one's just a little high. So I'll go and put air in one of the bags. What do you expect to happen to the bag that I put air into? So I'm going to fill it up and zip it closed. What do you expect to happen? Will it stay the
Sir,
same?
it will come down.
Go down because
It
I
will
put
go down.
I put air in it. Everyone, hop on the chat box. Let me know your guess this time. All right. This is wonderful data for me. I can see how you are thinking. This is very good. Thank you. I'll give you a minute to put your ideas in. Still got one or two people going up, but kind of most people are going, it's going down. All right, that's almost scientific consensus, we would say. All right. So I'm just going to zip open the bag just in the corner. And let's see what happens. Just want to make sure I'm not moving the wire at the top. That's all good. All right. That's annoying, everyone. That's annoying. We're going to have to do the experiment the other way around now. So I'll just have to balance. I should have taped this. I'll just have to balance it again. That's pretty good. And now so that it doesn't slide, because that ruins everything. Literally ruins everything if that starts sliding around. See how we go. Just going to move this out a little bit to get it balanced. It's pretty good. So we've got the seesaw balanced at the moment with this bag full of air. So I'm going to let the air out, which is the opposite of what we were talking about before. Which means those of you which thought it would go in one direction would think it would go in the other. So I'm just going to open the bag now. Take all the air out. Be careful not to move anything. And now see what happens. What do we see? It was balanced when it was full of air. It's now had all of the air squeezed out. What do we think? What do we think? Has it gone up, down, stayed pretty much the same?
So same.
It stayed pretty much the same.
Sir, same in word again.
The same.
I'm going with the very scientific answer, pretty much the same. So someone's going, oh, it's crumpled. That's not a fair experiment. Going, all right. Let's flatten it out. I think we're still with that very scientific result, pretty much the same. Pretty much the same. This balance is probably good to 1/10 of a gram. Not ultra science, but it's pretty good. So we just looked at a different version without the balloons, and a bag full of air is as heavy as a bag with no air. That's what this just showed us. If these are balanced when this is full, and it stays balanced when this doesn't have a lot of air, then putting the air inside the bag doesn't make that heavier. So that's kind of different from the one we saw with the balloons. So does that show air has weight, or does that show air doesn't have weight? I love this experiment.
Air doesn't have weight.
That's kind of what that's saying. That's kind of what that's saying.
But sir, what about the balloon experiment?
Yeah, what about the balloon experiment? That's my question. That's a good question, but that's my question. So this shows you one thing. The balloon shows you something different.
Excuse me, sir.
Yeah.
Sir, oxygen is it's heavier in the atmosphere and it goes down. So if the balloon is filled with oxygen, then the balloon will go down, and the balloon that is deflated, that will stay up.
So it's good to think about those sorts of things. It's good to think about those sorts of things. In the balloon activity, we used my breath for both balloons. So that was
Sir, in the polythene experiment, oxygen doesn't become heavier.
So the reality is oxygen, the average density of air in this room and the density of oxygen are not very different. And the density of my breath as I breathe it out is almost exactly the same. I take in a little bit of oxygen and I give out a little bit of CO2. It's actually CO2 which is heavier. Oxygen is about the average weight of air, a little bit lighter, but only fractionally lighter than, less dense than normal air. But my breath, as I breathe it out, has lost a bit of oxygen, but it's replaced it with some carbon dioxide, which is actually heavier. So the density of your breath is almost exactly the same as the density of the air around you. But again, with our two balloons, I filled both up with my mouth. So they had the same gas in each of the balloons. And when the air came out of one, the big balloon, the full balloon, went down. It said, I've got more mass. But with these, we're not seeing the difference. So Natish is going, they're made of different materials. Yeah, they are. How might that be important? Because that's another difference. So thinking scientifically, and I love that you are thinking scientifically and sharing your thoughts tonight. That's what tonight is about. I love that. So we should spot what things are the same, what things are different. Which of those things that are different are important? And that's when you're thinking critically, when you're thinking scientifically. And then you would test each of those things that are different to go, why is this difference important? Maybe it's not important. I could have used two different color balloons. That would be a difference. It's probably not important.
Sir?
Yeah.
The balloons were open at the top and the bags were open at the bottom. Does that makes a difference?
Yeah, maybe. It's kind of where the air got in, but they ended up all being sealed. So
Yeah,
I don't know
but
that.
if we leave the bag open, it still has air in it as the same as it is closed. We can just open it wider, and it still has the same air as if it is closed.
So I think that's an interesting thing to think about. So I've got these bags hanging upside down with the opening on the bottom. So one of the things we tend to think about is we're kind of used to carrying things like, buckets and boxes. You put more stuff in the bucket and the box and it gets heavier. And so we tend to think of the bag as empty. And if I've sealed that, now it's full. And so it kind of makes sense that it's heavier. Unfortunately, sometimes our common sense, lets us down. So we might think that bag is now heavier. We might think that bag is heavier, but if it was heavier, when does it get heavier? It's got as much air inside now as it does before, maybe even more air because I've opened the mouth wider. But it's not sealed, it's open, but it's full of air. Does that make the bag heavy? Most of us would probably think no. What if I have the bag sideways? Is the bag heavier now because of the air?
No.
No. Is the bag heavier now because of the air?
It may be.
Yeah, maybe. And this is going, okay, we're at the point now where we are really starting to try and think about what's going on. So if the air in here was heavy and was pushing down, if I took the bag away, why isn't the air here falling? Well, it's not. There's no breeze here. All right, the air isn't falling. The air isn't falling here. There is pressure, but the pressure is the same inside the bag, outside the bag. This is a very simple physical experiment. That's in many of your textbooks. And we don't get you to think about it. It hides some wonderful science. Let's go back. What was one of the differences? What's one of the differences between the plastic and blowing up the plastic and blowing up the balloon? Which was easier?
Blowing up the plastic.
Yeah, why? It was.
It had wider opening and it doesn't stick.
Yeah, maybe.
To each other.
Yeah, possibly. What about the rubber? Is it easier to blow up a balloon or do you have to stretch the rubber?
Elastic.
It's elastic. The balloon is trying to get smaller. You're trying to make it bigger. So when we're blowing up the balloon, we have to actually put more pressure in the air, not because of the air out here, but because of the elasticity, the stretchiness of the balloon. So the balloon is trying to stretch, pull back in. And so the air in the balloon is under higher pressure than the air in the room. And we know that because if I open the balloon's going to squeeze all the air back out. It's under higher pressure than the room. Here, the plastic bag is not elastic. And even though I might fill it up a lot, I might make it very full, it's not under pressure. It's the same as the air in the room. So when we're actually looking at this experiment, the thing which we almost all fail to recognize is whether it's a bag or the balloon, we are thinking about the air in the balloon. We're thinking about the air in the bag, but the room is still full of air. And so this is air floating in air. It's like you're in water. We just tend to forget about the air around us. And so if you get a bag full of water outside of the pool, it's heavy. You put the bag into the pool, the water in the bag doesn't count for anything because it's the same as the rest of the water in the pool. Okay, so a bag full of water out of the pool is heavy. In the pool, it's just the weight of the bag because the water isn't heavier than the water around it. And so it would just float there. Air is slightly different to water. We can compress it. And that's why the balloon shows you something which this doesn't. When you blow the air into the balloon, it's under more pressure. It's denser. We've compressed the gas. So the gas in here is actually heavier than the air in the room. So it's not buoyant. It'll sink. It'll fall. We say falling, but in fact it's sinking. It's air sinking through air. Here, when this is full of air, it weighs the same as the bag with no air because they're all in air. So when you see that demonstration with the balloon, it's not really showing you that air has weight. It's really showing you that compressed air is denser than normal air. This is showing you that air in air doesn't weigh anything. So it's a slightly different observation that you make with this. I'll stop there for a moment. Has anyone got any questions
Excuse me,
about
sir.
that? Yeah.
How can we show them that air has weight?
Well, that's a good question. A lot of that we would do using activities and demonstrations about air pressure and what happens when you remove air from one side of something. If you've got lots of sophisticated equipment, which most of us don't, you can go and take that bottle, take a bottle of air and weigh it in air, and then put the entire device in a vacuum and take the air out. And as you take the air out, you'll actually see that the air in the bottle starts to look as if it's getting heavier. It'll start to show that it's got a weight. And there are various other ways which we can look at to show that air does have weight. The balloon activity shows that compressed air is heavier than uncompressed air. So that shows that air has weight, but most of the time it's explained in a way that misleads students to think that if you put air in a bag, it would be heavier than a bag without air and it would sink. And that's misleading because that's not true. That's not true. Any other, but thanks for that question. That's something which we could do as another whole other session. Any other questions at the moment before we move on to the next activity? No?
No question.
Okay, I'm sure there will be a few questions there, but let's move on. Let's move on. As we know, time is always my master. So those of you at home, I haven't got you to go and do a lot of activities with me, but this one's different. This one's important. And I'm pretty sure, even without notice, you'll be able to find something suitable to join in. I just want you to go and get a small piece of paper, all right? Can just be a little bit torn off a notepad. Doesn't have to be white. It's just a little bit of normal paper, kind of about that size. A little bit smaller, a little bit bigger, not important. I'll give you all 37.5 seconds to see if you can find a piece of paper, and then we'll start the next activity. While you're doing that, I will go and take my sky hook down. All right. I'm assuming that most of you will have had a chance to go and grab a bit of paper. Now, my next question, and you can try this at home, but I want you to think about it before you do it. All right? It's the only request. Now, if I hold the paper in front of my mouth and I blow like this, and I'm holding the paper like that, what do you expect the paper will do? Some of my questions are very simple. This should not be very hard. So if I blow, what will happen to the
It
paper?
just moves away.
It'll move away.
Yes.
It will move
It'll
towards. It will move
It will
towards
not
you.
move. It will not move.
Move
Won't
towards
move.
It will
you.
vibrate.
It moves. It moves.
Vibrate,
It
vibrate.
moves. It might vibrate.
So it
Okay,
moves.
okay. Let's try. Those of you with a piece of paper, just try it. I don't expect to hear applause at that. I think most of you were expecting that it was going to do something like that.
Yes, sir.
Not extra special. That's okay. Now, if I hold the paper like this, so it's hanging over my finger, if I blow here, what do you expect the paper to do?
You will also fly.
The paper will come where the air is coming from. Like it
Will float.
will get straight. It will get straight.
Okay. All right. Sounds as if a lot of you have tried this, done this, or seen this. So let's try this again. So just, if you've got some paper there, try that. See if you can get it to happen. If I blow all the way up here, nothing.
Yes,
I
sir.
blow to the
Nothing is
side.
happening.
My piece of paper is kind of a little bit stiff, so it doesn't happen.
Too stiff? See if you can find something a bit more flexible. All right. So why does it do that? Why might it be doing that? I think I understand. When I blow here, it's just the air is hitting it. The air's got momentum, it's got energy, it's got a force, and it's going to push it out of the way. That feels like common sense. When I blow here and it comes up though, that needs a bit of explaining, I think. How would you explain it? Why does it lift up? Has anyone got an explanation for that?
The air when it moves it is taking the paper up. So this is because of the
What might it be, Redmi? So we're getting some discussion in the chat box. Getting some discussion in the chat box there. The breath displaces the high pressure region above the paper. Air pressure above becomes less than the bottom. So we've got some people which have, you know, thinking about changes in air pressure, changes in air pressure. So they're thinking there's high pressure on the top, pushing it down. At the moment, it's really just gravity. Air pressure in the room is pretty much the same everywhere. And so that seems to be they're suggesting. So Ronit's saying maybe the air released from my mouth has more pressure than the atmospheric pressure. So we normally understand that air will move from high pressure to low pressure. If you want the air to move, you've got to push it, compress it, it will flow from high pressure to low pressure. Ronit is suggesting that the air pressure in my mouth is high pressure. I've certainly got to get it out of my mouth, so I understand why you think that. And I think that's right. And then it starts moving. But the other suggestions in the chat box were making suggestions that we're creating a pressure difference across here because of my breath. Has anyone heard in their science classes of Bernoulli?
Of what?
Of Bernoulli.
Sir, excuse me.
Bernoulli. Bernoulli's principle. You may not have. I'm at a disadvantage. I don't know how old most of you are, so I don't know where you might be. Some of you are teachers, some of you are young students.
No, sir, not heard of it.
No, that's okay. It's okay. That's probably an advantage tonight. So later in your schooling, you may, if you do physics, you will probably come across Bernoulli's principle. And you'll probably be shown some activities about Bernoulli's principle. And they may talk about how an aircraft wing flies, or how an aircraft flies, and how an aircraft's wing works. Do any of you feel you understand how an aircraft wing operates? How does an aircraft fly, for example? Why doesn't an aircraft fall out of the sky? That always worries me when I travel. Read me.
When the aircraft flies at speed, then the air hitting it, the wings of the aircraft, they I forgot what to say.
Okay, that's all right. So when we think about aircraft flying, and you'll be shown diagrams of aircraft wings, almost everything in the normal science textbooks about how aircraft wings works, almost all of that is wrong. Almost all of it is a misapplication of Bernoulli's principle. Bernoulli's principle is a real thing, and it really works. But it's got very little to do with an aircraft. It's got very little to do with an aircraft. The normal explanation about what's happening here is that high-speed air has low pressure. All right, so that's what you will hear. And if you're in the right-shaped pipe, Bernoulli's principle tells you that, and it's true. If you get water flowing through a pipe and you have a constriction, it gets smaller and then bigger again. The pressure in the narrow bit isn't greater, it's actually lower. It's actually lower. And that's Bernoulli's principle. And it really works. But it doesn't work out here when we're not inside a pipe. But they will apply that idea to this, and that's wrong. They will suggest to you that where the air is moving quickly, you get low pressure. And that's a little bit like a couple of the explanations we had earlier. So if you blow quickly, they say the air pressure drops. So the pressure here is low, the pressure here is higher, and so it lifts. And that kind of makes sense. That's an explanation. The only challenge is what if I make a shape like this? I can still blow across the top. All right, I'll just put it out there so you can see the shape. I can still blow across the top. And so if Bernoulli was right, or if Bernoulli was the right idea to consider when we're looking at this, that would say high speed air creates low pressure here, high pressure here, it should lift up. Let's see what happens. Doesn't seem to be lifting up the way it was before, is it? Before, a little bit of air and it'll lift a lot. Here, even though I'm blowing high speed air, it's not lifting up. It's not lifting up. We're going to go over to my table. We're going to go over to my table and we're going to have a look at some other stuff to do with moving air. Okay. And I'm trying to keep a close eye on the time tonight. All right. So what I've got here, this is just a black plastic cup. Just use a black cup so you can see it nicely. And I've got a straw so you can see how I'm blowing kind of in a controlled way on what's happening down here. And I've just got a light little cotton ball, doesn't weigh anything. If I blow on it, it moves. So if I put the ball here and I blow through the straw, what do you think will happen to the red fluffy cotton ball?
Move away.
It will fly up.
Okay.
It will fly up.
The ball will move forward. It will not
It'll
fly
move
up.
forward.
It will move forward.
So
It will
we're
move
playing
forward.
air soccer, okay? I'm sure you kids have done that. What now if I put the ball, the fluffy ball, behind the cup and I blow here? What do you think will happen?
Shouldn't move.
The cup will move
Maybe it will
forward.
move.
Cotton ball will
It will move. It will
It will
move.
move, I guess.
I will
go
move.
further. It will not move. It will not
I
move.
think the air will split into two
Will
and
move forward.
Let's try.
not move.
The cup will move forward.
So I'll try it without the straw. It does move. So some of you were saying what you're kind of thinking was happening was the air would split around and come and join back up. And that seems reasonable. If you've seen water flowing in a stream, it goes around objects. That seems all good. What if I put the ball here, but I blow here? What do you think will happen?
It won't move.
It will not move.
I
It will
guess.
move sideways.
Because it
Move.
starts.
It will move.
What if I blow here, a bit closer to the cup?
Move, I guess. It's
It
very
will
light and requires a
move.
little bit of a.
Sideways.
It will move.
It will not go.
It moves.
Sideways. Yeah.
Yes, it
So
moves.
because once
moves
the
it
air
upwards.
comes out of the straw, it doesn't have to remain constricted. It moves towards all the directions.
Well, I don't know that it's moving in all directions, not just by itself, but that's an idea. And so if I have time, whenever you have an idea, I'm not going to say right or wrong, we're going to test it. So what you suggested was as the air comes out of the straw, it doesn't have to go in the one direction, it can go in all directions.
Yes, so like pretty much like a funnel cone.
So as I blow from here, do you expect all of them to move?
Yes, sir.
Yes, sir. Yes.
So I'm not saying you're right or wrong, but I'm testing it. So it looks as if at least over this distance, it's going, most of it's going pretty straight. And if you want to think back to Newton, something moving in a straight line is going to keep going in a straight line unless it's acted on. Now, there's all sorts of things happen when things are flowing. So if I go far enough back, there is a little bit of spreading for sure. But it's always good to test your ideas, and you can do those tests quickly and easily. So here it does nothing. Here it seems to move. What if I put the ball there? That seems crazy.
Shouldn't move. Well, maybe it will.
It will not.
You're
It'll move, I
beginning
guess.
to be,
It'll move.
you're
It'll
beginning to
move.
become very
It
suspicious
move.
of every question I ask, and that's good. You should.
It's not moving.
Almost.
Did move.
Just a little bit, that far round. So we can use that to tell us that the air is turning that much of a corner. And so before we saw that the air pretty much goes in a straight line, a little bit of fanning out, but not a lot. So for the air to get over here, the air has been pulled around the corner. It's been pulled around the corner. And I mentioned Newton a moment ago. Something moving in a straight line is going to keep moving in a straight line unless something acts on it, a force, to get it to turn. And one of Newton's other laws tells you that every force has an equal and an opposite force. So if the air is being pulled in one direction, so if the air is getting pulled this way, it's being pulled that way, it's going this way, ends up going that way. So if a force is doing something to make the air go this way, there's got to be an opposite force. Where do you think the other force is? What's the other object in the story?
Cup.
The cup.
Yeah.
There is something about the cup, because if I put the ball here and blow, the air isn't turning a corner. The air's turning the corner because of the cup. I'll behave. So the air is turning the corner because of the cup. So there is something about the presence of the cup which is creating a
The cup
force.
is reflecting the wind.
Say again? You said something about the cup deflecting?
The cup. Yes, sir. The cup is
So-
deflecting.
So is it deflecting? Deflecting feels more like, you know, something hitting something. Here, the air is going past the cup. So it's not like I'm using the cup to deflect the air.
Does the
The
cup
air-
exert some force on the air?
Yeah, it is. It is. And we don't have enough time tonight. We could spend a lot of time. There is another property of a gas, which is viscosity, stickiness. So when air moves, it also pulls other air with it. So even though I'm just moving this air, the air that's next to this picks up some of that motion. And the air that's next to that air picks up some motion. And so air that's moving past an object will feel the object, and it will tend to stick to that stationary object. So even though the air here is trying to go quickly, it will feel the cup. So the layer of air closest to the cup will stick to the cup, and that will slow the air down next to that, not completely, and the air outside of that will get slowed down a little. And so you can think of all of the air moving forward, these ones getting slowed down, the other ones still going at their normal speed. They end up being pulled around the corner because of the viscosity, the force, the stickiness of the air on that cup.
it pulls the air around the corner. And so if the air is being pulled in one direction, Newton says every force has an equal and opposite. So if the air is getting pulled this way by the cup's got to be being pulled in that direction. Okay, cup's got to be being pulled in that direction. You don't see that move because they've got a big magnet in the bottom, so it stays put. If I put a light cup there and blow past it, you will see it gets pulled over and then gets blown away. You might, if you look really quickly, you'll see it just comes in towards that. And that's the force of lift. It is the aircraft wing drawing air and forcing the air down. It's even more complex than just we've seen here with these cups, but that's the basic idea behind it. That the air flowing over the cup gets pulled down, and the aircraft wing is designed so it captures a lot of air and draws a lot of air down very quickly. And it's that force, the air being thrown down, that means that the plane, equal and opposite forces, is pulled up into the air. So Bernoulli is a real thing, but it really doesn't apply to things like aircraft wings. It applies in plumbing and other closed systems. But when you're thinking about what's happening here, just think about where the mass is going. The mass of air is being pulled down, or in this direction, pulled that way. So there'll be a force in the other direction. So that's one of the things. You'll see it badly explained in just about every textbook. And there's 3 or 4 different wrong explanations about aircraft wings. If you're particularly interested in that science, go to NASA's website, where they take you through kind of all 3 bad explanations, which you will find common out there in the textbooks. NASA is also rather, I was going to say scared. So I'll say scared. NASA is also, even NASA is a little bit scared about giving you one answer about why an aircraft wing flies, and that's NASA. So they will tell you on their website the 3 or so answers that are wrong. They're not, even they aren't going to tell you what the right answer is.
I searched, Googled it, and I found that the first answer that came up was from NASA's website. Its title is Principles of Flight, Bernoulli's Principle, NASA.
So it would be interesting to see which site you're looking at. So NASA is keen on their education site to let you know which of the explanations are wrong.
Official website, actually.
Yeah, it's NASA. They will tell you what's wrong with the various common explanations or misexplanations of it. They won't give you one answer about how an aircraft flies, because the answer is it's complex and it depends. It depends on what the aircraft is doing. It's not one principle. But the big thing which I've shown you tonight is the main principle that's behind all of the common demonstrations that you'll see. Technically, if you want to search for something, this principle is better explained by the name Coanda, the Coanda effect, which talks about how you end up drawing air and throwing it down. So that's a better explanation for most of the time for how most aircraft fly. All right, so Natisha asking, does the cup exert some force on the air? Yes, it is sticking to the air, and the air is sticking to the cup. So just imagine me, big, heavy, like the cup, and you small and light like the air, and you go running past me, and I put my hand out, and for a moment I grab your hand as you run past, and then let go. You're going to end up changing direction. And whilst you change direction a lot, I'm still going to get pulled towards the direction or away from where you're being sent. All right. So it is very much a kind of a can be understood very much in terms of Newton's principles. All right, let's see where we're going. We've got about 30 minutes left. Let's try and do 2 more. What if there was a cube instead of the curved surface? Great question. You ask good questions, it just makes everything go slower. It's an interesting shot of my bookshelf. So if it's a good question, I think perhaps I've thought of that before. So here is a cube. If I put the ball behind the cube and I blow, what do you think will happen?
Same thing. It doesn't move.
It's not moving. Not even just behind there. Even if I put it this way around, maybe
There was a ball beside it, and the air hit the cube, and the ball
the other
beside
one,
it flew away.
but not behind it. What if I put it this way around?
It should work.
Nothing is here.
Nothing.
Yeah.
The nothing.
So again, if you put the ball here and blow past, it's like the piece of paper that I showed you with the bend in it. That's too sharp a corner. The air won't go around the corner. It will just keep going straight. And because the air isn't pulled around the corner, because the air doesn't change direction, there is no force on this. There is no force on the paper. And this is one of the ways to tell the difference between Bernoulli's explanation, as it's often misrepresented, which says fast moving air is low pressure. This is low pressure, this is high pressure, you'll get a force. But it just doesn't happen. If anything, it goes away. And so that's a clear demonstration. I'm not saying
How
Bernoulli
does
is wrong.
Sharp edge prevent air from taking it away?
Because the force of the air sticking to here and the momentum of the air is too great. And so the only part where it's trying to pull the air down is just this very small corner, just the very small corner bit.
Reduces the surface area. Okay.
Yeah, over which it can act. Whereas if I'm doing this, then the air has a lot of surface area sticking and it can pull it little by little by little, getting a little force each time it turns it. So this gives you all of this area to get that turning force or that lifting force. This only gives you this much surface area to act on. And so the air doesn't get changed direction very much. And if you don't change the direction of the air, then you don't get the complementary force. So if you don't end up changing the direction of a ball, you don't get an equal and opposite force to it. So it's not me that's saying Bernoulli is wrong. I'm just going, here is the observation. If Bernoulli says high speed air is low pressure, this says that explanation doesn't work. And so we should certainly listen to any hypothesis, but a hypothesis is only as good as the observations that it can explain. And so Bernoulli doesn't explain what's happening here. So Bernoulli happens, but it's not happening here. It's not important here. All right, let's look at another, probably even slightly more baffling activity. And I'll just set up another camera, see how we go for time. I won't have as much time as I'd like to go into the next activities, but we will do them. All right, just for information, those are the tanks I set up last night, and I haven't done anything with them, okay? So you can just see the blue water that was in the tank A. Ice was in the salt water. The ice is all dissolved. The blue has mixed a little bit in the top layer, but just see how little has mixed with the
Yes,
rest of
sir.
it.
It's still on the
Yeah,
top.
you see the edge here is a little bit furry, a little bit soft.
Yes,
It's
sir.
not a sharp edge. That is diffusion. All of this, which we saw happen in a few seconds the other night, that's convection. Convection works really quickly and can work over big volumes. Diffusion is really quite slow, and it only really works well over small distances. And a lot of people will see mixing happening and they will call it diffusion, but it's not. This is diffusion, and it'll take a month or more for this blue to get to the bottom. And that's not just because the water is salty. If I'd carefully put fresh water with just a little bit of blue fresh water here and kept the temperature in the room the same, it would look very much the same as that. So let me just put these somewhere where I'm sure to kick them over later tonight and make a mess in my study. Again, what we're going to look at is we're going to come back to ice. So we did ice and density and convection the other day. And I used some salt water to get some density changes. And I've got three bottles. I'm now going to put on some rubber gloves because I'll be playing with a bit of ice, which is probably still very cold. So if you see some black hands turning up on the screen, we haven't changed presenter. I've just put on some rubber gloves so I can actually handle the ice long enough. So one of the ideas we had heard of last night was someone was talking about freezing point depression. Salt depresses the freezing point, and maybe that had something to do with how fast the ice melted. And we're talking about my Canadian friends. Here is some crushed ice, just normal ice. I've just hit it with a hammer. And I'm going to try and put as similar amount of ice into each of these jars. The ice has been made, sorry? This in here is just,
it might crack.
Here, it'll be fine. Thanks for your concern. But again, I'll take the risk. I'm wearing rubber gloves. I'd be more worried if I was putting hot water into this glass.
Because it will contract, and if it contracts,
it certainly will. It's a small risk with this glass. And I'm less worried about that possibly happening because I have done this experiment in these glasses before. But if this is the first time you're doing it, you would be wise to be careful. All right. We're doing science, but we're not going to publish the results, so we don't have to worry. You might see a very small black hair in here. That's because I have a dog with black hair, and everything in the house is covered in black hair, if you look close enough. All right, now let's go and see what the temperature in these jars is. I've got some digital thermometers. I was working to try and get some larger displays organized so you could see it more clearly. So the ice has been in my small freezer. It's been out for a little while in the esky, just keeping it cold. The room here is at about 20.
Reading in Celsius or Fahrenheit?
Celsius, yep, Celsius. If you can see that well, you can see that well, and I will read the numbers out to you as well. But just in case you're skeptical and you don't believe that I'm reading the right numbers, you can always look. So all of these should come down to about the same temperature. The thermometers aren't super accurate, they're not super scientific grade. So they might read to within about a degree the same. We'll see how they go. There's this kind of misconception that, you know, if you've got a digital readout, it must be very accurate. That's not true. Not even close. Just means it's got a digital readout. I'll try a second thermometer and just see if I can get one which is a little more consistent with the others. And what we're going to do in a moment, I'll just see whether or not this one reads better agreement with the other thermometers. It's looking better. I'll take that one. All right. If we're arguing the difference of 1 degree, it's not going to be a big deal. So the thermometers are now reading about 1 degree. Now the ice is going to be much colder than 1 degree. The thermometers are reading partly the temperature of the ice and partly the temperature of the water that's melted around the ice. So it's slightly wet ice. You can kind of see that perhaps. There's a little bit of water in there with the ice. So mostly ice, but a bit of water. And that's pure-ish water, it's Canberra water. So it freezes at about 0 degrees, close enough. And what we're going to do now is I've got some sodium chloride, table salt. I've got some sucrose, which is just table sugar. And I've got a little bit of ammonium sulfate, which I don't know why that would be on your table, okay? We might use that in the garden as a fertilizer. It's an ammonium sulfate, it's just a simple salt. I'm going to add about equal amounts of all of these ingredients to this ice water, but it's mostly ice mix, and stir it round. What do you think is going to happen? What do you think is going to happen?
So is the sucrose just grounded sugar?
So it's just table sugar, just plain sugar. That's all.
So you've got it grounded.
It's sorry, say again.
So you've got it grounded.
Yeah, so it's grounded. So it's crystallized sugar. Yep. So just seeing if I can find some other spoons. Good. There. So what's going to happen, do you think? I will add about the same amount of crystals to each. And let me start with the sucrose, which is just table sugar. And I'm going to put, and I'll mix them in a moment. I'm going to put 2.5 teaspoons of sucrose in there. I'm going to put, and at the moment they're all reading either 1 or 0. So table salt, 1, 2 and a bit, 2.5 of the sodium chloride and the ammonium sulfate. My carrots just won't be quite so big this year, but that's, I guess I'm prepared to make that contribution. And some of the ammonium sulfate into the last one. And now, let's just see, let's get that in a little bit. Lighting's not great.
Sir?
Now I'll just, yeah.
Did it mix the same quantities of these things?
Yep, pretty much. So that's the sugar mixed.
So you got 1.5 spoon for the sucrose and 2.5 for the.
I think I did 2.5 for the sucrose
Hello,
as
sir?
well. Yeah.
Yes, you did 2.5.
Yep. It's you people are. I wouldn't want to get something wrong. You people are watching me like a hawk to make sure I get it all right, which is fine. You should. If I get it wrong, you should let me know. All right. So the sugar has gone to -2 now. The salt's gone to -4. The ammonium sulfate's gone to -1. I'll just mix them up a little bit. It's one of the reasons I use these steel thermometers. I can use them as mixing sticks as well. So we're at -2 for the sugar, -6 for the table salt, -3 for the ammonium sulfate. So I'm full of questions. Why? They're all getting a little colder. Table salt's getting a lot colder, down to -7. Down to -7. And if you could see, I'll show you in a moment, it's getting so cold further down that in fact I'm getting frost. Water is freezing out of the air in the room on the outside of the bottle. The ammonium sulfate's gone to about -4. Sucrose is still about -2. The table salt's gone to -8.
This temperature is going on decreasing.
Yeah, down, down, down. Later, in a month's time, I could show you a graph of this happening as it happens, but I haven't got all the equipment sorted out. But you can draw the picture in your mind. It's still, yeah, it's still going down, still getting colder. -9. Woohoo! I like low numbers.
Wow.
I'm just blowing on the outside of the containers. I'll bring this bottle over in a moment, but there's lots of ice forming on the outside. It's down to -9. Down to -9. -2, -9, -5. -10. Yes, double
Wow.
digits. -10. You can, with the right sized chunks of ice and slightly larger crystals of salt, you can get down to about -15, -16 doing this kind of activity.
So one question.
Yeah, just one.
Yes, sir. So
Start with
the temperature is increasing and decreasing, but the white is increasing and decreasing in the same ice.
You're saying it's increasing and decreasing?
Yes, sir.
It's just decreasing.
It's just decreasing.
It's just decreasing.
Down to -11. -11. -2. So the sucrose, the sugar, kind of went to -2, pretty much stayed there. The ammonium sulfate's kind of down to -5. So it's been coming down slowly as well. Give that a little bit of a stir. -6. I'm going to spoil the perfection of the experiment. I'm just going to put a little bit more ammonium sulfate in.
So this wasn't uniform.
Sure, I've spoilt the experiment, but we weren't going to publish it in a scientific journal anyway. Oh, here down to -12. We're getting close to a record tonight.
So if we keep it for more and more time, so will it go very low?
Well, I think -12 is already pretty low, but it will eventually stop. It will eventually stop going down, and putting more salt in.
And it go to -20?
You'll be lucky to get it to -20. It'll depend on how cold your ice is. If I put this into a thermos, because at the moment heat is coming in, as this is very cold. It's 30 degrees cooler than the room.
It's summer in Australia, so it's
It's summer here. It's 30 degrees. It's nearly 40 degrees cooler inside there than in the room. Okay, so there's a lot of heat going in there. So if I put this in an insulating styrofoam package, protected it from the heat of the room, it might get down to kind of -15 or so. So we're at -12. That's a pretty good result. You can, I don't know whether or not you can see there. Perhaps you can see there the kind of the crystals reflecting as I turn the bottle around. crystals of ice which are formed on the outside of the bottle because it is so cold it's actually freezing the water vapor out of the air. Now, there will be several kinds of experiments. Oh, minus 13, 14. And we're almost at my record, minus 14. Pretty good. That's solid. That's good. That's a big result, or a small result. The ammonium sulfite now is down to minus 9. And it's now starting to get ice crystals forming on the outside of the bottle. It's that cold.
And the sucrose?
Not even close. It's just minus 2. It's just wet on the outside. So water is condensing on the outside, but it's certainly not freezing. It's not cold enough. Too much. It's not cold enough, and the heat is going in fast enough to stop it freezing. So that's pretty good. So I'm kind of left, as I always am, left with some big questions about why that happens. Why does the temperature drop? What's going on? And why is there a difference? Because we spoke the other night about freezing point depression, and that's a real thing. But freezing point depression is pretty much the same no matter what you put into it. So the same amount of sodium chloride will have the same depression as the same amount of any other kind of salt. So the freezing point depression is the same. But just depressing the freezing point won't make it cold. And that's what we often forget. We kind of look at those experiments and go, oh, freezing point depression, you've added salt to ice and something's happened, and you'll say freezing point depression. But I'll just quickly change camera, and I've got just a couple of minutes to do this and my favorite, all-time favorite short activity. So let's just look. I'll try and do a quick drawing here and leave you with a puzzle, which you can get in touch with me and talk about afterwards. Think of this as water and its different states. I'll take that out. So water, and I'll adjust the camera in a moment so you can see. So water, and this might be the boiling point of water, pure water, and that's 100 degrees. And pure water, the freezing point
0 degrees.
Is 0 degrees. And when we put something like table salt into water, we almost always say it depresses the freezing point. The same is also, I'll come back to that in a moment. It depresses the freezing point, which is also the same as it depresses the melting point. That's the same thing. Freezing and melting is the same point. It depresses the freezing point. It also increases the boiling point. So this is pure water. This is water plus salt. And until you get really, really concentrated salt, the more salt you put in, the more this moves apart. So this is one of the fundamental principles of, if you like, physical chemistry. So let's just look at this bit that's happening down here at the bottom. Just make sure I've got you in shot. So pure water freezes at 0. If I've got semi-salty water, the freezing point might be minus 10. All right, might be minus 10. So if I've got some ice, and ice itself is always pure ice, when ice freezes, all the salt and the rest of it comes out, so it's always pure ice. If I've got some ice at minus 5 degrees, so I've chilled my ice down to minus 5, if I surround it with pure water, what will happen? if I surround it by salty water, what might happen? Can I have ice at -5 in salty water? In salty water, at -5, water is still liquid. It doesn't turn to ice until down here. At -5, ice, at -5 in fresh water, it's ice. So the freezing point depression we often think of as making it easier to freeze. It doesn't, it's the opposite. It makes it harder to freeze. It's got to be colder before it freezes. And that's why my Canadian friends put salt on snow to go and move it down here so that the snow, which might be -5, can now become water. There's another thing happening. This happens, this is true, this is real, but that's not the only thing that's happening. There's a second thing which happens when I mix the salt in with the ice. It's not freezing point depression, it's something else. And that's what I will leave for those of you that are interested to go and search for yourself, because I think I've just got time to set up and do before we finish for the sort of the valediction. I've got time to set up and hopefully do my all-time favorite activity. And this one is kind of just fun. Well, it's not just fun. I think it is. I think it's very special. I hope it's special. I haven't done it with this equipment. I've only just finished making this equipment this week. So what I have here, is like a dish. It's kind of like a small pool, circular. It's about 10 millimeters deep. It's got a little lip, and I've got a plate that I can fit into the top so that I can turn it round, but it's not going to slide all over the place, okay? So it's like a little round swimming pool. And now the really tricky bit is I've got some glucose syrup. So it's kind of like clear honey, all right? Very viscous, like honey, slow moving. And I need to go and pour exactly 153 milliliters of this into here. Let's hope I get it about right. I love working with fluids and liquids. I'll just give that a moment. And while that's spreading out, I've also mixed some food coloring in with some glucose syrup over here, all right? So I've got glucose syrup colored, otherwise it's identical, just a few drops of food coloring.
Why do we always use food coloring in our activities and not some random paint?
Well, it helps you see what's going on. It's good to visualize, and it does make the photographs look better.
Yes, I'm talking about why don't we use some other kind of paint that are available for?
Oh, you can. There's nothing special. It's just a color that I can put in with the liquid. So if you've got other colorants, other things to color it, so you can see where the liquids are flowing, feel free to do that. Nothing special about it. It's just colored, and I can get it easily. For you, you might use turmeric, or if you've got other food ingredients which are brightly colored, or ink.
They're talking about watercolors, for example.
Yeah, for sure. Some of those will be clear. Some of those will be kind of pigments, so particles. So they'll add color, but you might not be able to look through them. But you're a smart kid. You're thinking about how you might do those sort of activities yourself. So we're getting close. Some of these things can't easily be rushed. Let's just try that. I could have set it up beforehand, but you wouldn't have seen how I set it up. We are very nearly ready. And I'm just going to put some Australian dollars under there to go and level it up a little. I think we're getting close to the edge. Just put in just a little bit more. That's too much, but that's all right. Okay, I'm going to give that a moment to flow out. Now, some of the things we've been doing have been mixing things. You saw the other night, we put blue coloring in with the water and it all mixed together. Do you think if I waited long enough, the blue liquid, do you think the blue liquid in here is going to unmix? Unmix, go back to being a nice concentrated blue spot. Will it just will it just randomly reconcentrate? I'm not getting answers.
No.
So
No.
I think you're going, no, you're an idiot. Of course it won't. That just never happens. All right. And that's one of the laws of thermodynamics. We say that systems tend to become more disorganized. And so
we organize the way.
So if you put a drop into a bucket of water, it will tend to spread out everywhere. It's not going to come back and make a concentrated drop at some stage in the future. And that's described as entropy. It's a different kind of concept, but it's a way of describing the amount of order in a system. And it's often referred to as the second law of thermodynamics. I'm always a little cheeky. I don't think that the law is really a law that you need to follow. It's more of a guideline. So normally you don't see that happening, but it doesn't mean it can't. So let's see if we can break the second law of thermodynamics. Be a bit risky tonight. So I'm just putting a bead of blue colored glucose syrup across there. I really should have sort of just made the Indian flag, I guess. But, you know, perhaps if I did a bad job, that would be a diplomatic incident and I'd be in trouble. Even though my Indian friends would probably try to forgive me.
So is this food coloring viscous or was it?
The food coloring, so this is just a few drops. What I'm putting on here is just more of the glucose syrup into which I've added a few drops of food coloring. So it's not just food coloring, it's 10 drops of food coloring, which I've put into about 30 mils of the glucose syrup just to color up some of the glucose syrup. But apart from a little bit of food coloring, that's exactly the same material, same properties as the clear glucose syrup. Let's just go and put a nice yellow circle around that. That seems reasonable. And because I like blue,
white,
all right. I hope this works because you've been very patient. All right. So there's that. That looks pretty colorful on there. I seem to see Hema has dropped in to check that we're doing good work. I hope she thinks we're doing good work. We're certainly doing very colorful work tonight, Hema.
Post it on Facebook.
All right. On there, quick selfies. All right, now I'm just going to lower this disc on top of the glucose syrup. I'm going to try and do it carefully and slowly from one side, just so I don't get any air bubbles trapped underneath it. Works just so much better if there are no air bubbles. That's pretty good. That's pretty good. All right. I'm happy with that. That's this should work fine, but we never know. So we saw with our blue liquid, it doesn't unmix. So we see where it is. We're now going to mix this up. And as I move it around, we can see that it's sticking to the top, it's sticking to the bottom. It's all getting spread out. All right. That looks pretty mixed up. All right. That also is pretty. I'll take a picture of that.
Looking like a painting.
It's like a painting. Science is like a painting. But what happens now if I try to unmix it? Is that even a thing? Can we break the second law of thermodynamics? That would be a thing, wouldn't it? If we can break one of the laws of thermodynamics.
It's coming back.
I think we just broke the second law of thermodynamics, everyone. I hope you don't let the newspapers know. That's going to have us in trouble. Here, the Australian consulate funding me to break laws, but I guess they're only laws of thermodynamics. Let's try that again. That's pretty. So we were looking tonight at lots of things, some of them to do with fluids and how fluids flow. And we're talking about viscosity and how that sort of helped planes get lift. Wow, that is super pretty. Even if I can't unmix it, that's worth a photograph. Let's see if we can unmix that, shall we? Is that impossible or just unlikely? I don't know, we're going to get there. Still feels impossible these days. But wow. All right. I reckon that's pretty good for unmixing. I reckon that's pretty good for unmixing.
How's that happening?
That's a great question. That's a great question. I'm going to check in now with our masters at the Science Centre. How much extra time do you have? Would you like to go and start for the questions, the Q&A, the valediction at the moment, Suman? You're still on mute.
Hello, good afternoon. Am I audible?
Yes.
Yes, sir.
Yeah, we had a small valediction session. Afterwards, you can also communicate with the steward with his mail ID, or you can also ask your queries to the Science Centre directly. We're happy to answer your all queries. And I once again welcome all dignitaries and participants. Today we have Hema Singh Rance Madam with us. Due to her ill health, Madam Hema will not speak. And on behalf of Regional Science Centre Bhubaneswar, now I would like to express my deep sense of gratitude to Odisha Vigyan Academy and the Australian High Commission New Delhi, Australian Consulate Kolkata. Without their support, it could not have been possible to organize such a mega event. I am personally thankful to Professor P.C. Misra, President Odisha Vigyan Academy, Engineer Bhagat Charan Mohanty, Secretary Odisha Vigyan Academy, Daniel Sim, Deputy Consulate General, Australian Consulate Kolkata, Madam Hema Singh Rance, Manager Culture and Public Diplomacy, Australian High Commission New Delhi, and Madam Angelina Nayar, Australian Consulate Kolkata. I'm happy to share that responses are overwhelming. We got responses about 2,500 registrations, and our digital outreach touch milestone of 20,000. Now I would like to listen from the dignitaries if they can share their experience and suggestions so that we could disseminate scientific knowledge to the larger part of the society to promote science, technology, innovation, and creativity. In this regard, I would like to request Madam Sivli Mitra, Communication Associate, Principal Scientific Advisor Office, Government of India, if you share her thoughts. Madam Sivli Mitra is Madam Sivli Mitra.
Hello, hi. Thank you. I hope everyone can hear me.
You're coming through fine.
Yes, ma'am.
Thank you. So congratulations to the Regional Science Center Bhubaneswar, Odisha Bigyan Academy and Australian Consulate General based in Kolkata on successfully organizing this mega science fest. I'm really thrilled to know there were about 20,000 people who you could reach out to through this event. So it has been a quite exciting time, I'm sure, for all of you guys. You heard a space scientist, an astrophysicist, an astrobiologist, a science illustrator, a teacher who uses origami to teach math, and then, of course, Dr. Stewart, who believes in using simple materials to teach very complex concepts. I cannot remember any of my lessons in school were even nearly as exciting as what you showed over here. And I think I would have had a better understanding of Boyle's law if I had attended one of your classes. I congratulate all the speakers on that. So having fun and learning something at the same time is something that was a very far-reaching idea when I was in school. I think that goes for many of the organizers of this event. So all of us understand how important such events are. So congratulations to everyone for having organized this. My advice to the attendees will be to spread the word that there are science communicators from across the country. So reach out to them, invite them to your schools. Now it's a lot more simpler as nobody has to fly down to your town or cities to give these lectures. We can all meet each other virtually. So invite them and have fun and learn. Thank you very much.
Now,
Over to you, Stuart.
now, may I request Dr. Stewart to address the gathering?
Thank you so much for the opportunity. I feel as if I've had more than enough time in one way to address the participants and our dignitaries here this evening. But as we found each evening, I just had more I wanted to share. We never finished all of the activities. That's a sign of me. I will always have more. I think for me, I hope the participants, if they take away one thing, it is to be comfortable to make observations and to try and think about answers and explanations themselves. It's not that listening to your elders, to your teachers, is a bad thing. There's nothing wrong with doing that. But there are other skills that you need going forward. Skills in critical thinking. Whether you go into science or not, you need to think critically, to look at the observations for yourself, look at the information or the data yourself, and to think more deeply about it. Take a moment to think more deeply. Whilst there is a lot of prestige and pride in being to answer a teacher's question with a quick answer, that is fine, but there is a deeper understanding. So I I am less interested if you can tell me what Newton's second law is. I never bother to remember which is the first or the third. And in my workshops, I often talk about Newton's seventh law, and everyone gets a little confused. I'm not too worried about the naming of these laws, but about, do you really understand the principles? So I work to try and encourage you to think, ask yourself hard questions, and take the time to work out, how would I answer that? Don't always go to Google and get an answer. As I said at the beginning, if I was training you to become a marathon runner, telling you how long the course is and then driving you to the finish line does not make you a runner. You do not get respect for hopping out of the car and crossing the finish line. The real respect comes from you learning how to do the run. The same will be true after your schooling, when you graduate and enter the real world, and your employers, your community, more than your employers, will need you to solve new problems. Problems that, you know, Google might give you some of the clues, but Google doesn't have the answer. We've got complex problems, new problems, problems that are specific to where you're living, to your communities, and you will need to work out how to solve those problems. And getting the strength for that problem solving starts now. It's not something which you tack on when you finish university. You should always be, all the way through school, develop some of those skills. So hopefully through the series of workshops, I know some of it might have been frustrating, that I was asking you questions and we weren't answering them. I hope I leave you with many more questions than I gave you answers, and that your curiosity will get you to keep thinking about them into the future, both as teachers and as students. Leave a bit of time for the questions. Don't always fear an unanswered question. I look at them as treasures. So again, I'd like to take the moment just to wrap up and thank deeply and dearly the Australian High Commission and the various consulates, particularly the Consulate General in Calcutta, for this series of workshops, for the opportunity to engage with many educators across India this year. COVID has made many things harder. For me, COVID has made reaching my friends and colleagues across India so much easier. We've made the change, and we look forward to that continuing in the future. So go forward, treat your questions as treasures, and don't fear them. And thank you all for the opportunity to interact with you.
Thank you, Dr. Stuart. And this is the time to make forceful end. And before we end, I, on behalf of Regional Science Center Bhubaneswar, respectfully thank you all, especially the dignitaries like Madam Hema Singh Ranji, Shivli Mitra ji, all my respectful teachers present here, and my dear students from all across India, and all other dignitaries left behind. Thank you all at the same time for attending this valediction ceremony, as well as the workshop presented by Dr. Stuart for all of us. It was a nice program. We have taken the feedback. Everybody enjoyed. Especially we in India, we are habituated to answer very fast, but not to think that much. Our children, you might have experienced, Dr. Stuart, before you present something, they are ready to answer. Now, this sort of attitude is going to be changed henceforward. We are actually motivated to think more rather to speak more. And this has happened because of the examination-oriented preparation and competitive examinations our students are to face in future. But this workshop changed our eye to another direction of science learning atmosphere, and that is called the thinking mode. So I essentially request all my dear students here present to change your attitude gradually, not at the same time, because you know Indian situation needs something more. So to think, and then to publicate your research. So thank you, Dr. Suad, and thank you all dignitaries. And we come to an end. Hope to meet again in another platform. Thank you all.
Thank you. Good evening.
करके सब सेशन को कवर कर लो।